Dr. Ambrosio Ortiz, I don't know if you're already online. Can you hear us?
Yes, good afternoon, Doctor. Good afternoon. I'm sharing my presentation.
Please, let's test it to avoid any issues.
Thank you.
Perfect.
Well, first of all, I want to thank...
Give me a moment, I'll introduce you. Thank you. Well, good afternoon, everyone. To continue with today's presentations, at this moment, it is my pleasure to introduce Dr. Ambrosio Ortiz Ramirez. He is part of the National Polytechnic Institute, and today he will present his paper titled Evaluations of European Options by Monte Carlo with the Heston Stochastic Volatility Model. So now go ahead, Doctor.
Well, thank you very much, Doctor. First of all, I want to thank the organizing committee for accepting this presentation. I am, as you mentioned, at the PLE Institute. It is an honor to be here with all of you. I see there are many enthusiastic young people. I am also from the provinces, but I have built my career here in Mexico City, and I hope this talk will be useful to you, young people, and to our audience listening, because this presentation, this model I will present today, is part of research I have done with thesis students and other colleagues. Let's begin. What are we going to discuss today? Well, we will address the evaluation of European options with the Heston Stochastic Volatility Model from '93, a seminal article, and we will do it by Monte Carlo. So for this, we will cover the theoretical characteristics of the model, as well as the evaluation method of the seminal Heston article. And in this context, the Monte Carlo simulation refers to generating artificial paths of the underlying asset's weight and its variance over time, like in a system of stochastic consciousness with correlation. So, with the paths we generate, we can obtain prices of European options or other types, depending on the payoff function. So, for this, we will propose the system's discretization in an Euler scheme, and we will execute a Monte Carlo exercise with variations in the model's parameters with their corresponding effect on the distribution of the underlying and its variance. So, some background on the content of this presentation. We will look at the introduction, methodology, and some classic examples, I suppose classic simulation examples. We will see some definitions of financial derivatives, and then move on to present the Black-Scholes Merton model, which is a standard in the industry and academia. We then move on to the Heston model, where I present the structure and the Monte Carlo method. So some results that we will see more in the practical part, some conclusions. So as you already know, Monte Carlo, in its origins, was known under more generic methods like statistical sampling, and the name comes from Stanislaw Ulam, Neumann, and Metropolis, who used this reference to a famous casino in Monaco, where Ulam's uncle used to go. Money to gamble. So the problem that the earliest use is that of Enrico Fermi, in which he used a random method to calculate the loss of the throne discovered by Chadwick. Monte Carlo methods are fundamental in the simulation of the Manhattan Project, which is a precursor to the atomic bomb, and although they were limited by the computational tools of that time, they were used to achieve interesting results. Monte Carlo methods are sampling methods based on probability theory. They are supported by a determined number of trials from which information of interest is extracted. For this reason, they are based on two results, you know, which are the and the law of large numbers. The central limit theorem, as you know, if we have a session of independently distributed values with the same mean, the same variance, then in theory, it converges in distribution to a standard normal and the law of large numbers, while the more relations we make of a certain process, then it converges to something that this convergence can occur in probability. Classic examples, we have the law under the curve, a function, as we know in the Riemann integral, we can approximate increase upper limits, lower limits, and make the limit of those characteristics that Riemann literally has. And let's say it's a third, not a number, but we can also do it with Monte Carlo. What we do is generate n pairs x, y. Of uniforms from which we count the points below the curve, and then the integral is approximated to accumulation between the number of points below the curve and the total number of points, which is the separated area we see in the next graph. Here, we have the domain of the function, we do the integral, we enter the program with the condition that they are less than or equal to those we have, and we do the calculation. Then, another classic Monte Carlo problem is calculating pi, in which we have a square radius 1 and radius equal to 0.5. We enter the equation in the circumference, we generate the variables x and y uniforms in aluminium 0, 1. We count only those that meet the inequality. So let's see here, this inequality, then you can fit the circle as pi times the square of the radius here, if r equals 1/2, as we saw up here, then the cyclic area is given by this equation here. We have pi as an approximation of 4 times the area. So what do? Well, this simulation is like throwing dice at this little square, and what we do is calculate the favorable cases and total cases. So pi will be the greater the number of samples, the better the approximation will be. Then we enter the part of what is a financial derivative, which is a private contract whose value depends on an underlying asset, which can be an interest rate, a stock, a commodity, a currency. Derivatives range from forwards, futures to nonlinear contracts like options and swaps to more complex products like structured notes or exotic options. What is a financial option? It is a contract that, for the payment of a premium, gives its holder, if the buyer, the right but not the obligation to buy or sell the underlying at a determined price. These underlyings can be goods, stocks, stock indices, currencies, futures, interest rates, etc. Two concepts. The first is where the possibility of buying the underlying at a strike price is acquired or granted, called a call or purchase option, and it can be a long position if the call is bought or a short position if the call is sold. The option where, on the contrary, we sell the underlying at an exercise price is called a put. And similarly, it can be a long or short position if the put is bought or sold. In this way, the position we have in options is independent of the product's creation, meaning the possibility of buying or selling the underlying. In summary, if options are bought, you have a long position in a call or put, or if options are sold, you have a short position in a call or put. Thus, the payoff of a call option is given by GT, where T denotes the expiry, which is fib by the maximum of I and K, unlike two quantities where Fi is an indicator variable that can be -1 for a short exposure and 1 for a long position. So, according to the definition of a sale, we have the same payoff function, which is phi by K, S sub T, where we have phi, the indicator function, and it is the maximum of the difference between the exercise price and the final price. In this way, the payoff option is not the inverse of a call, nor is it the inverse of a put. What are the approaches to option valuation? Well, we generally have three: the probabilistic, partial difference valuation, and Monte Carlo. In the probabilistic approach, the expectation is the payoff option under a risk-neutral measure, which is to use a Black-Scholes in 73. The other is to use partial difference equations, where Merton's approach through a portfolio posits positions in an option and an underlying, and through mere changes in the prices of both assets, derives a partial inferior equation, in which through variable changes we arrive at the heat equation. Through the heat equation, we return to that variable change and find the price of the call and the put. The other approach is by Monte Carlo, where in a risk-neutral world, that is the value of a contingent asset like an option, is the expectation of the discounted fundamental payoff, martingale under risk-neutral measure. And this same probability makes all risk factors like stocks, indices, currencies, cryptocurrencies, etc. move, put in quotes, move, because the fact is that they are martingales. They move with the risk-neutral measure, making the counted processes martingales. And martingales is a concept widely used in mathematical finance, in which it is a process that is zero-sum or has no trend. In general form, what are the assumptions of Black-Scholes Merton? First, constant interest rate. The market operates continuously. Transaction costs and taxes are zero. The stock does not pay dividends. Short sales are allowed. And also the stock's volatility is known and constant during the option's life. Here the concept of volatility is important because in the original paper, volatility is constant. So those criticisms led to more development on that concept. And here I present the formulas that appear in any finance or mathematics book, or some references that come at the end of this presentation. We see the price of the call given by equation 1, the price of the put by this equation, and what phi d is, the standard normal distribution function, what d is and what d is. Then from here, some criticisms that come from the unit. We find empirical evidence that there is asymmetry that was cut. This comes from the fact that the volatility of the underlying asset is constant. So in practice, these implied volatilities of options for different terms and prices are not constant and tend to be in the form of a smile, or smile which is a grimace. What is implied volatility? Well, the volatility that makes the implied difference in the market and Black-Merton equal to 0. Seminal articles Hull-White 87, Hull-White 88, and Stein. These papers were pioneers in the sense of considering that volatility was no longer constant and was driven by a stochastic process. I'm referring to the smile patterns, where if we plot on the x-axis a quantity that is K, about what is known as moneyness, and on the y-axis the implied volatility, we observe patterns of implied will, the first referring to the smile and the second to the smirk, where we see that here it is symmetrical in terms of volatility, whereas here a decreasing function of this quantity K is observed over S known as smirk, Heston model. The process is by a Brownian motion. The volatility in this case is driven by an Ornstein-Uhlenbeck type process and also presents mean reversion that we consider there. The Cox-Ingersoll-Ross model, a process associated with an interest rate model, and the Wiener processes are obviously correlated when we set the covariance of the first Brownian motion and the second, which is equal to rho dt. Here the correlation is constant. We can also present the Heston model. Observe here the first equation that models the changes or returns of the process. Mine is a trend, and the root of V, which is the volatility. Now it depends on time, and we have the first Brownian. In this case, the volatility is given by an Ornstein-Uhlenbeck process number that you know in physics, whereby making a variable change and applying Ito's lemma to a process followed by the variance, we arrive at the equation that describes the volatility. In this case, we have d sub dv dt is equal to kappa by theta minus v sub t by dt plus sigma by root of v sub t by the second Brownian, where this beta is equal to kappa over 2, delta is equal to delta over 2, and theta is equal to delta squared over kappa. Here there is an important consideration about this type of processes, where this equation you see here, k by theta greater than sigma squared. This is known as the effect condition. It is important because if you notice over here we have the root. In this Feller condition ensures that if we always want to have positive values for the variance, it must be fulfilled that when making the inequality, it must always be covered that 2 kappa theta is greater than sigma squared. A formula similar to Black-Scholes is obtained to evaluate a call option. The option price is obtained by calculating the probability that a call option expires in the money. What does in the money mean? That the underlying at maturity is greater than the strike price in order to exercise it. It says, although such probability cannot be calculated directly, it can be obtained through the inversion of the characteristic option of the logarithm of the underlying asset's price. Then we arrive at a semi-analytical formula for option evaluations, using a stochastic model where it is similar to ST by P minus K by P of T by P. The put price is obtained through the put-call parity test given by equation number 6, and we observe here that these quantities are proofs that the option expresses conditional algorithm of decent weight x equal to algorithm CT equal to x and over probability B sub t both at time t. We arrive at the expression of the PDJ, which are the probabilities. We have j equal to 1 over 2 as mentioned earlier, and moreover, these PJ are given by this equation number 7, where we observe here that this integral, when done in practice, and as there are different papers, this real part needs to be discretized, moving from this integral to numerical integration methods. And these depend on whether you use Gaussian quadrature, Simpson, or other similar ones. So it is the closed formula. We now move on to the Monte Carlo part, where the model, as we saw, is represented by a system of stochastic differential equations where they are correlated, and moreover, to obtain, we can use analytical methods or simulation, since it is a classical process. So what we do is generate random values that result in a different trajectory in each simulation by changing the coefficients. As we will see in the notebook, rho and sigma describe the behavior of the trajectories to show their effect graphically. So what do we do under a risk-neutral measure of the Heston model can be proposed through two equations, 8 and n. As you can see here, this delta t represents a change in time that is associated with this equation. We have here also that we change for r, that is the risk-free rate. Here, usually when one is doing the simulations, one says a coherent value, and I put here risk-free because in practice, when one wants to do it on some underlying, it is risk-free credit, because we use CT's curve that gives us the price bender. So how do we perform the simulation? We do C as the spot price and B as the initial variance. We have correlated normal variators, and we use here the Koleski expression and generate trajectories variations of the parameters. Here are two observations when doing the simulation series. One of them is the speed with which the volatility reversion process converges, the second equation in the Heston model, which is the root process, and the second is the possibility of generating negative values of BT even when the Feller condition is met. Then, to solve this, we have two ways. Use the maximum between 0 and VT, which is truncation, or use reflection, which is replacing V with the absolute value of VT. Another approach is to simulate the variance, which is the Cox and Ross process, and it is a G squared, and there are quite a few developments on that. What is the procedure? Well, we have here the parameters, S, RQ, sigma n, delta Tm, the initial variance, and the volatility parameters that are given by the user. And also, if it is a call or put option, what do we do? Do we break down the time, please, in T?
Tell me, you have 5 minutes left, please.
Yes, of course. So we do like Cholesky, and what does it do? We transform here two matrices. We do the distribution and step number 2, step number 3, where we see here that when we pass it to a programming language, we pass VT equal to the maximum between 0 and VT, where the epsilons are normal, are we? So if you allow me here, you can see my screen. Can you see it on screen, Doctor?
Yes, I can see it. Thank you.
So the notebook that is available to those who want to write to me, or I send it to you, Doctor, we have here, we propose the model, here we do it in Jupyter, or we can also do it in Google Colab. The packages, the initial parameters. We define a function as the methodology says to do this, the values we start S and B. The Koleski one, the initial values of the underlying, and the volatility. This is where we do the DLW, we do the Koleski one and multiply. We do the dot product between the Koleski one and the normals, because we said it has correlation, and also the discretization, as the equations in the precision say, well, they are here, the process that runs to the underlying or the asset. And for the variance, these equations are the ones that provide, note over here that we can put it twice, one here as the maximum between V, or the maximum between Vt and 0. In this way we call the function, and see what it gives us with 100,000 trajectories, number of rows, number of lines. Who is that note over here? They all start at 100, but what interests us are the final values. The final values, which are these. S is a structure, and come here when we are doing the simulation, how we generate the cloud of trajectories. We start with S equal to 100. And what we have here is the discretization into 252 equal parts. So for each moment, as it is said in probability, each WW generates a random variable. And for each trajectory, we generate an observation of that variable. That is what we do n times. We also generate, we have here B and Y. And then the process for the variance, for the payoff function. Here we bring the average of the payoff function and 0 to present value and calculate the call price. If you look over here, it has the payoff function. We bring it to the present with the risk rate, the payoff function, and it gives us the call price, the put price. We graph the integrated variance versus the relative price. Obviously, as we are making correlations, this is known as a copula. I'm not going to talk much about that, but well, here it gives us the variations in the asset and the volatility. We generate the trajectories and we see the final values. What it gives us are the final values. We make the histogram and we see that it is negatively skewed. That is the bias. Here we see the normal in red and green, the distribution. We also make the graph of the final values of the variance. And we see here that it is asymmetric. We can do more experiments. That is, here I can change the row. If I change here the RHO or the sigma, it will give us different distributions. For example, if here I change it from negative and change it to positive, I give it to execute the simulations at n steps with those new parameters, then we will see that the distribution changes. That is, it changes the way we are seeing how it is done. The effects of the correlation parameters influence the distribution of returns. I think it's stuck here. Well, I'll move on to the conclusions. Doctor.
Yes, thank you very much.
So yes, we did a Monte Carlo simulation with European functions, and we assume that the model parameters are given. Other approaches can be likelihood. Loss functions, we create the histogram of final values of S, sub T, and V. What do we observe? That Monte Carlo is based on statistical sampling techniques, concepts of probability and stochastic processes. Monte Carlo simulation is very versatile and has applications in physics, chemistry, economics, finance, cognitive sciences, etc. And what are the most important findings here? And this process means that theta pulls towards an average. V is pulled towards a long-term value theta at a rate determined by the speed of mean reversion kappa. What do? We created a system of stochastic differential equations. We performed the discretization. That is, we divide the time horizon into a number of time steps and observe that when doing the comparative statics, the arrow coefficient models the skewness and the variance coefficient sigma models the kurtosis of the return density, respectively. And well, that's all from me. There are some references. Thank you, Doctor.
On the contrary, thank you very much. A round of applause for Dr. Ambrosio, please. We have very, very limited time because we continue with the plenary after this presentation. We might only have time for one question, please. Which side do we have?
Hello, good afternoon. My name is Oscar Flores Marino. I have some questions. What are the advantages of using your model, the Heston model, and the implied volatility in the option, if you have already compared it with the options directly in the derivatives market? Or have you done backtesting to compare the volatility given by, for example, some brokers to certain options, or the volatility calculated with the Heston model? And also another question would be, why don't you use the funding TI, the software rate, or the LIBOR for the risk-free rate?
Yes, thank you. Interesting questions. Well, the first one, what are the advantages of using this type of model? Well, the first is that, well, if you search the internet or look at part of what I've done, but I'll explain it here very simply, it's the following. The Heston model provides implied volatility curves that are very similar to what the market gives. If you graph or download the price vectors, those volatility curves will be very similar to what we observe in the market. Now, the issue, as you say, is Regarding the risk-free rate, there have been changes. You refer to the SFR, which is a sovereign rate, offer rate night, something like that is what follows. Why is this rate used now in the markets? Well, it turns out that for operations that are
Well, we can't hear you. Could you open your microphone?
Sorry, it's because you muted me. Well, sorry, we were saying about the risk-free rate that is used. I put CETs there. But what the student or colleague refers to is that this rate, that OFR is used for operations in dollars. So if one wanted to value options on the exchange rate, then we would no longer use the risk-free rate. But the difference between the local risk-free rate minus the foreign one, that's what the theory says to do. Evaluation under the absence of arbitrage. And the last question you asked me, well, if we have used backtesting, backtesting has several exceptions. One, in terms of backtesting in market risk, is in general backtesting refers to measuring the efficiency of a value at risk model. That is, if you calculate the VAR for 1 day and do your market at T+1 and make the difference, if your bar predicted in quotes a loss that a certain position in a portfolio may have, then it means that if it exceeded that loss, it means that your model is not incorrect but is subject to external effects. That is, it exceeded your loss to what your VAR predicted. Then backtesting is also used in trading. That is, you do a part of saying backwards. If your trading model anticipated market movements, and there is a lot of literature on that, right? If I answered your questions, colleague.
Yes, well, he says yes. Thank you very much. So once again, a round of applause for Dr. Ambrosio Ortiz Ramirez.
Thank you, thank you. Thank you, I'm at your service. Doctor, anything? Any information you may have or concerns your students may have?
Of course, we thank you very much. And, well, we will continue in a few moments with the plenary, the second plenary of the day. So I ask you not to leave your seats.